Hey, welcome to the Explainer. Today, we are tackling a question that seems simple, but has a totally mind-bending answer. Why do the building blocks of our universe look less like little planets and way more like some kind of surreal, abstract art? Let's dive in and decode the bizarre beauty of electron orbitals. You probably remember this from science class, right? The atom as a neat little solar system. But then quantum mechanics comes along and shows us the reality is this strange, intricate cloud. The journey from that simple model to these wild, complex shapes, well, it isn't just a change in the picture, it's a fundamental shift in how we understand reality itself. So, to really get to the bottom of these shapes, we first have to wrap our heads around the single most important rule of the quantum world. And believe me, it's a principle that completely rewrites what it even means to be a particle. And here it is. It all boils down to this. At the atomic scale, everything is a wave. I mean, we experience the world as solid, right? But an electron trapped inside an atom, it's defined almost entirely by its wave-like nature. Now, I know, trying to picture an electron as a 3D wave can be tricky. So the best way to get this is to build it up from simpler ideas, starting in just one dimension with something we all know, a guitar string. Think about it. A wave traveling through open space can have any wavelength it wants. But what happens when you pin that wave down at both ends, like on a guitar? Suddenly, it can't just have any old wavelength. It reflects back on itself, and it creates this stable, repeating pattern. These specific, allowed patterns are what we call standing waves. And that confinement is the absolute key. Only a handful of wave patterns can fit perfectly between those 2 points, creating these distinct, separate values. This is quantization. It's the reason a guitar string plays clear, specific notes instead of just a smear of random noise. A really crucial feature of these standing waves is something called a node. It's a point of complete stillness that doesn't move at all. You see, the simplest wave has no nodes between the endpoints. The next one up has 1, the next has 2, and so on. And the number of nodes is directly tied to the energy of the wave. More nodes means higher energy. Simple as that. Okay, let's jump up to 2 dimensions. Think about a drumhead. The exact same rules of confinement apply, but now the nodes aren't just little points anymore. They become lines, either circles spreading out from the middle or straight lines that cut right across it. So we've gone from 1D strings to 2D drums. You see where this is going, right? We're finally ready to make the leap to the 3D space around an atomic nucleus and apply this very same logic of standing waves to the electron itself. But here's the big twist. For an electron, the wave isn't a physical thing going up and down. No, it's a wave of probability. Because of its weird quantum nature, we can never know exactly where an electron is. Instead, its wave tells us the probability of finding it in any given spot. To see it, we basically square the wave's amplitude, and that gives us a static map of where the electron is most likely to be. And those high probability regions, that's what we see as orbital shapes. They are literally the 3D standing wave patterns an electron is allowed to make when it's trapped by the pull of the nucleus. Each unique shape is just a different, quantized energy state. And these shapes, they aren't random at all. They follow this really precise and elegant set of rules, kind of like a recipe that we call quantum numbers. Just think of these 3 numbers, N, L, and M, as an address for every possible electron state. The N number sets the overall energy level, kind of like the size, but the real magic behind the shapes, that comes from L and M, which tell us all about the geometry and orientation. The number L is the one that directly defines the shape. It does this by setting the number of angular nodes. Those are the flat planes that slice right through the probability cloud. So L equals 0 gives you an S orbital, which is just a simple sphere with no nodes. L equals 1 gives you a p orbital, with 1 node cutting it into 2 lobes. And D and F orbitals just keep going, adding 1 more node and 1 more layer of complexity each time. So once L tells you how many of these nodal planes you have, M tells them which way to point. For a p orbital, which has that one single plane, M just orients that plane along the x, y, or z axis. And that's how we get those 3 distinct dumbbell shapes you see in chemistry class. You know, a good way to picture this is with a yo-yo. An M value of 0 means the orbital is pretty much aligned with the vertical z-axis, just like a dangling yo-yo. But higher M values mean there's more angular momentum around that axis, which causes the probability lobes to fan out horizontally, kind of like that same yo-yo when it's spinning.
So now we know that orbitals are standing waves of probability, and they're defined by quantum numbers. But there's one last secret. Turns out the familiar dumbbell and cloverleaf shapes you always see in textbooks, they aren't the whole story. Get this, the raw mathematical solutions actually produce these donut-shaped things called complex orbitals. The dumbbell shapes we all know are called real orbitals, and we actually create them by mathematically combining the complex ones. So why do we do that? Well, while the donuts are the pure fundamental state, the dumbbell shapes point neatly along the x, y, and z axes, which makes them way, way more useful for visualizing how atoms actually connect to form chemical bonds.
So why do electron orbitals look so weird? It's because electrons aren't little particles orbiting a nucleus. They are waves that are confined by a nucleus. These bizarre and beautiful shapes aren't paths. They are maps of probability, the elegant, quantized patterns that just naturally emerge when you trap a wave in a very, very small space.